a drug that will kill the coronavirus. Okay, questions about today or from last time? I did hand back your review sheets. There is an answer key online. I would strongly encourage you to go through that. If you have any questions, bring them up or put them on Piazza or come and see me, and we can go over those. So any questions about today's or other materials? None? All right, then I will start the conversation with this. This is left over from Friday. So both of these reactions are oxidation reactions. What kinds of reagents do I use to take a primary alcohol to an aldehyde? What kind of reagent would I use to make a carboxylic acid out of a primary alcohol? Any suggestions?
Could you use PCC to get the aldehyde?
What else do we have that are oxidizing reagents? So we could also use Swern or what's called Des-Martin periodate. Those three reagents will stop at an aldehyde. Okay. And so these reagents are considered to be mild oxidizers. Now, if you want to take a primary alcohol all the way to the carboxylic acid, you're going to need a strong oxidizer. So what kinds of examples of those do we have? Camino-4, chromium trioxide, H2SO4, peroxide would do that. Sometimes even oxygen will do that, although most likely oxygen would be nice to oxidize an aldehyde, so I won't necessarily put it there. Potassium dichromate, K2Cr2O7. Those would all be in the classifications of what I would call strong oxidizers. So these are so that's the classification of strong oxidizers. So maybe we should take a step back here and say, all right, what are we talking about with oxidizing of alcohols? What we're talking about with the oxidation of alcohols is this. We take a primary alcohol and we can oxidize it to an aldehyde. We can further oxidize that to a carboxylic acid. That's sort of the oxidation scheme for a primary alcohol. For a secondary alcohol, I can only oxidize that to a ketone. So secondary alcohols are only oxidized to ketones. And then a tertiary alcohol, since you have 3 alkyl groups attached to the carbon, they can't be oxidized, so those would give no reaction. Because I can't make a carbon-oxygen bond with 3 other carbons attached to it. That's 5 bonds, which is still illegal. So, in terms of our oxidation schemes, we can go primary alcohol, aldehyde, carboxylic acid. So if I use one of those strong reagents, a strong reagent will go all the way to a carboxylic acid. And if I use the PCC or Des Martin or Swern, those will stop at the aldehyde and they will not oxidize an aldehyde. And something as simple as oxygen can oxidize an aldehyde to a carboxylic acid. If I'm looking at a secondary to a ketone, everything will do that. Mild and strong. So if you use PCC with a secondary alcohol, you'll get a ketone. So all of those oxidizers will oxidize a secondary up to a ketone. Okay. So those are the oxidation schemes, and it's just the specific reagents. You can use any reagent you would like. Now, the 3 that stop at the aldehyde are special simply because they stop at the aldehyde. That's their job. So the other ones are just kind of run-of-the-mill oxidizers. So if we look at, we can talk about the environmental friendliness of these oxidizers. CaMetal-4, probably not that bad. Chromium trioxide sulfuric acid is what is called the Jones reagent. And with that goes potassium dichromate. These are both using chromium 6+ to do the oxidation. Now, in terms of environmental friendliness, they're not. Because chromium 6+ is probably cancer causing. And if you've ever seen the movie, and it's kind of dated, Erin Brockovich, it was about 2 things: lawyers and the environmental issues around chromium 6, even though they didn't talk about it that way. Because chromium 6 has been used as an anti-scaling chemical in pipes to keep them from building up scale on the inside. That's different than what we want to happen in our water pipes. We want scale to build up in the water pipes, because the scale that builds up in the water pipes protects the water from the metal that makes up the pipe. So in Flint, what they did was they took away the compound that caused the scale to form, and then the water became really acidic and stripped all of that off, leaving the pipes to then get lead infused into the water. So in general, we want to keep the scales on drinking water pipes, but in an industrial situation, you probably want the pipes not to scale up. You use chromium 6. If it escapes, it goes into the ground, then it goes into the groundwater, and that's what that movie was about. Chromium 6 is a bright orange color. It forms chromium 3+ when it's done, and chromium 3+ is green. And chromium 4+ you can go over to CVS and buy in a supplement. which says all heavy metals are not the same. It depends on their oxidation state. So in that movie, that was a Julia Roberts movie. And Erin Brockovich was a real lawyer. She shows up on TV occasionally. They showed this big pond of green. That was a chromium 3+ that had reacted with the air, that somehow got into the groundwater because they just kept a pool of it lying around, which happened in the older days. It's like these huge ponds of coal, of washed coal remnants that live down in West Virginia that are just waiting to break and flood towns and all sorts of things. So some companies don't have the best environmental practices, but that company got sued and tons of money were made, but it was all about chromium. So these are not particularly great. If I was going to use these in a synthesis of a drug that I wanted to sell as a drug company, I would be barred from using them in like the last X number of steps of the synthesis, because I could never prove to the FDA that I got all the chromium out. Same thing's true for mercury. When we did mercuration, demercuration, not a favorite reaction either. So these heavy metals are being phased out. And so things like, you could use things like bleach, which is hypochlorite, and acid will also do this oxidation. That's a more environmentally friendly way. But you don't want to mix bleach and acid in your cleaning of your bathroom, because it'll produce chlorine gas and you'll asphyxiate yourself if you're not careful. All right, because chlorine gas is not compatible with lung tissue and skin. That's World War I gas that they used as a war agent, or I don't know, mentoring a student from one of the high schools around here. I've only seen her once, but she's working on this report on nerve agents and chemicals of war, and I'm supposed to explain the chemistry of it when she gets to that point, which I don't know, so that's going to be fun for both of us, I guess. So, yeah, don't mix bleach and acid unless you're in the lab trying to oxidize a primary or secondary alcohol. And then it's very environmentally friendly, relatively speaking. Peroxide would also be one that you could use. So there's environmentally friendly and environmentally not so friendly reagents. The problem with the PCC, and you could use PCC just as an abbreviation, PCC stands for pyridinium chlorochromate. And that has a nitrogen in a benzene ring. We put a proton on it, so we form our pyridinium. Started out pyridine, it's now pyridinium. So we add HCl to it and we get pyridinium in the chloro part. The chromate is just simply CrO3. So if you mix those together, you get PCC, which it's kind of like the Lindlar reagent, where I'm tuning down the reactivity. That's what I'm doing here. But the problem is it's still chromium-6, which is bad. So that's why you have these other reagents, which you can just name SWERN. SWERN uses DMSO as one of its reagents, so DMSO is much more environmentally friendly. And the Des-Martin periodate has like, I think, an I3 in it, a periodate type molecule. Those two are much more environmentally friendly than chromium-6. Des-Martin works pretty smooth. I think we had an aldehyde a couple years ago. We had a primary alcohol we needed to oxidize to the aldehyde, and it went really, really smoothly. As long as you turn the separatory funnel upside down and quickly vented it. because the pressure built up much quicker than we thought. So it sprayed stuff everywhere. On first time, second time went right. So those are the reagents we have choices of. So you want to stop at the aldehyde, choose the mild ones. These are all examples of mild. These are all examples of strong. So you want to stop at the aldehyde, use a mild reagent. Got a secondary alcohol you want to take to a ketone? All of these will work. Want to form a carboxylic acid? Use the strong ones. So those were in Friday's, Friday's reading. I put a couple problems for Friday, but since I didn't go over it Friday, I didn't include it in the quiz. However, it will be on Wednesday's quiz. So that's oxidation of alcohols. All right. Questions? Other questions? Well, then let's go to today's. I start with that tertiary alcohol, and I would like to make those two different alkenes out of it. Take a minute, discuss, look back through your notes if necessary, and I feel like that might be necessary, and then give me a couple possibilities to do each one of these two transformations. I want to make the most substituted double bond. I want to make the least substituted. What should I use?
Is that right? So then you have like electrons and and then you have to use a phase. But then because like, does that make sense? I don't know, but I usually think these two are the first one. And I think we're both that's exactly what I was chips. That's how I do investing because they're toxic and like to do that, like double bond, that's not really ideal. I know my ass like I know in the mornings when
What do we want it for dinner?
Okay, do we have any ideas? Do we have any ideas about either what reagents we might use for either of these reactions? None at all? Julia?
Do you use like an acid or like an H plus first to protonate the alcohol?
Okay. So you want to protonate the alcohol to form an oxonium ion.
Yeah.
Okay. Then what?
You're asking me or the class?
It's up to you if you want to pass on that. I mean, you were the one that suggested the H plus.
Well, no,
Is that as far as it went?
No, but
Okay. What happens next then?
we thought you'd use like either a sterically hindered or a small base to form a double bond.
Okay, that's interesting.
Would it just like leave and then it would go through E1 to form the bottom thing?
Let's take both of those possibilities. So let's say the water leaves and I form a carbocation. And then that's now my alpha carbon. There's a beta carbon here with a hydrogen, a beta carbon here with a hydrogen, and then of course there's a beta carbon there with a hydrogen. We'll call these beta hydrogen 1 and beta hydrogen 2. And we're all okay with the fact that this beta hydrogen 1 is the same as this beta hydrogen 1. They'll give the same product. So then the question is, which hydrogen am I going to lose? 1 or 2? Which one is going to give me the major product? Or both? One. I see a 1.
Was this like in his situation or my situation?
This is his first. We'll come back to yours in a minute. So what mechanism is this going to be if it forms a double bond? E1. So this is going to be an E1 mechanism. I forget. E1 produces what kind of alkene? The most substituted. Always? As long as there's hydrogens there, beta hydrogens, it will. So in this case, which hydrogen am I going to lose? 1 or 2? 1. So I'm going to lose H1. So I'm going to lose H1 plus to then give me the most substituted double bond. So if I want to use the lower pathway and I want to make the most substituted double bond, let's use H plus. I should probably throw something else in. Maybe a little. Triangle. Maybe a little H plus and some heat. Would let me form the most substituted double bond. That's an E1 reaction, but is also called a dehydration reaction. Now, my next question is, where did the H plus come from?
H2SO4.
It came from H2SO4. So it has to come from H2SO4. Why not HCl? Or is HCl okay?
HCl would have to carbon cation.
So if it's a HCl or HBr, the Cl or Br minus would add to the carbocation, and I would end up with not E1 but SN1. So I got to use sulfuric acid for this. So if you go back and you look at your notes, dehydration is using H2SO4 and heat. So if I want to form the most substituted double bond here, let me go ahead and use H2SO4 and heat, and that will give me that product by that mechanism. Right. Does that make sense to everybody? Now, that's the easy one. The more difficult one is, how do I make the less substituted double bond then? So I want to go through the top pathway. And it was suggested that we'll still protonate the oxygen, but now we will add what to it? What do you want to add to it? You want to add tertiary butoxide. Because we know tertiary butoxide does what? It forms the least stable or least substituted double bond because it goes after the hydrogen that is least hindered, the beta hydrogen, except that won't happen here. Right? What's the tertiary butoxide going to do? It's going to deprotonate the oxonium ion. The oxonium ion's an acid. So it's going to deprotonate the oxonium ion. Great. So I haven't accomplished my reaction because it just deprotonated the oxonium ion.
What if that after the oxygen ion gets off? And the more molecule will have a carbon ion.
It's going to form the most substitute double bond first.
Oh.
See, here's the issue is that if you want to do that, you have to have the tertiary butoxide and the H2SO4 at the same time. Well, what happens there? It just deprotonates it. Or better yet, it protonates the base. All right. Well, can we solve that problem? Well, let's just not protonate the alcohol. Great. Then I could say, you know what? I can use the NH2 minus, and I could do the same thing. And what would I form? Would I form the most substitute double bond if I use the NH2 minus? What's the NH2 minus going to do? No. It's going to deprotonate the OH. It's going to deprotonate the OH. So that I end up with this. How do I know that? Well, because N minus is a stronger base than O minus. So the NH2 is just going to deprotonate. Now, let me go back up a step and say what's going to happen there. I'm going to get an equilibrium where the tertiary butoxide is just going to deprotonate the other alcohol. Now, we didn't do either one of these reactions last semester.
Using a bulky base.
Any base that I use is going to be protonate DOH. That's the conundrum that we have. Last semester we talked about using these bases to form alkenes. Did we ever use an alcohol? We never used an alcohol. What did we use? Instead of an OH being there, what has to be there? What kind of leaving group? What were our leaving groups last semester? Halogens. So maybe a Cl or a Br needs to be there. Well, okay, that's great. I can use tertiary butoxide if I want. And if I do that, I make the least substituted. If I use NH2 minus, I form the most substituted. But the critical part here is it wasn't an alcohol, it was a chloride. It was a leaving group. OH doesn't leave. Now, the way we made OH leave is do what? Protonate it. But now what I want to do is I want to use strong nucleophiles that are also strong bases. Well, they aren't compatible with protonating the OH to make it leave. And those bases will deprotonate an alcohol. So I can't use tertiary butoxide with an alcohol, I can use it with a halide. And I can use it with the tosylate esters that were in the reading and videos for today. So the whole topic was turn OH into a good leaving group. Last semester we protonated it. That's no longer compatible with these reagents. I need to turn that OH group into either a halogen or a tosylate ester. Now the halogen is pretty straightforward. Maybe. I want to do that reaction. I want to convert OH to Cl. What should I use?
Chloride?
No, I just want the chloride. I don't want the tosylate group. I just want to replace an OH with a Cl. HCl. Right, I'm having that sense of deja vu from like 15 minutes ago. Right? HCl, we're going to protonate the OH, this is the tertiary. The water's going to leave, the chloride's going to come in and add, and so I can change it over. Easy. Secondaries would be easy as well. Add HCl to an alcohol, secondary alcohol, as long as it's not going to rearrange, and the secondary carbocation is stable, which it should be, I can substitute an OH with a Cl by just simply using HCl. Now, the problem comes in when I want to take a primary alcohol. So I want to take something like this. I would like to convert it to a Cl. Or I'd like to convert it to a Br. But what about the primary system? The primary system is going to have issues. Right? I can go ahead and I can add my H+. That's going to protonate to form the oxonium ion. Then the oxonium ion is going to leave. No. Because if it left, what kind of carbocation am I making? You're not allowed to do that. So what happens? The chloride's got to do what? Chloride's got to come in, attack that carbon, kick the water off, and then I can make that. Can we do that? Sure. Takes 45 minutes of reflux. right? We all know that because we did the 45 minutes of reflux last semester. Only it was a bromide instead of a chloride, and it wasn't HBr, it was sulfuric acid providing the proton and then Br from NaBr. Right? So can you do that? Yes. Is it difficult? Yes. So we need other reagents to be able to convert OH to Cl or OH to Br. And we have those. Those reagents would be something like this. SOCl2, PCl3, and PCl5. And then there are the SOBr2 equivalents along with PBr3 and PBr5. These reagents, their only goal, their only purpose is to convert an OH to a Cl. That's their only purpose. What advantages do they have? They have the advantage that they work a lot smoother with a primary reaction, the primary alcohol. They tend to work a lot smoother. Why didn't we use them in lab last semester? Well, they have issues. They're moisture sensitive. There's usually pyridine added to these things to absorb the hydrogen once the H plus comes off of the water. And pyridine is a reproductive hazard mostly for men. But it's not, it's nasty stuff regardless of your gender. So we don't use these, but if I wanted to, these would be better ways to do this primary reaction. They also are better because they won't undergo rearrangements. So if I had an alcohol where if I add the H plus, I'm going to form the carbocation and then it's going to rearrange, I would want these reagents in order to do that. But what's the purpose of these reagents? They're to convert an OH to a leaving group, the leaving group being the halogen. So if I took my original molecule and I made a chloride out of it, then now I could use NH2 minus if I want to make the most substitute double bond, or I could use tertiary butoxide, but I cannot do that with an alcohol. I need to convert the alcohol to a leaving group. The other reagent you can use is a sulfonyl chloride or a tosyl chloride. Okay. So if you looked on Piazza, I actually put a short couple of pages of why are we using tosyl chlorides. So if you didn't, I would strongly encourage you to do that. I'm not putting as many videos on Piazza, depending on the topic, because I'm trying to create a document that then you can just download and use as your notes. So that was the purpose of today, was to make an OH a better leaving group. First is to use those reagents to convert them to halogens, and then also use the tosyl chloride. Okay. So I'll send an email out specifically for what Wednesday's quiz will be over. It will be over oxidizing reagents, and I could very easily ask you these kinds of reactions in terms of converting to a chloride, tertiary butoxide versus NH2 minus. Plus I can ask you tertiary butoxide plus an alcohol, and I will guarantee you I will get somebody making a double bond out of that. Okay, it's not, you want to make sure you don't fall into that trap. All right, if you have questions, like I said, put them up on Piazza, come see me. Otherwise, we will start with a quiz on Wednesday and go from there.